Okay. No, no, not at all. Yeah. Okay, so I guess it's still morning. Yeah. Good morning, everyone. So, first of all, thanks to Edgar for this very kind introduction. Well, I have never, as a student, attended this spring college, but I always wanted to come back as a lecturer. You know, I always dreamt high, higher than what others would do typically. So thanks to Edgar and Matteo and others that I could come back as a lecturer here. So what I'll do is that I'll talk about this synchronization. So the first lecture will be largely a PowerPoint presentation. I'll show you a range of physical contexts in which you see this effect of synchronization, just to get an idea what it is all about. What are we talking about? And then what I'll do is that I'll use it as a framework to learn about many topics in classical and quantum statistical physics. Topics that some of you are probably familiar with, but I hope to also introduce you to topics that you aren't familiar with. These are techniques that allow you to study synchronization, but also these are techniques that allow you to study a whole range of physical phenomena in statistical physics and nonlinear dynamics. So they are not very tied to synchronization. Synchronization just gives you a way to learn these topics in a simple manner. Okay. So the first lecture will be about synchronization. What all physical contexts in which you encounter synchronization. I'll show you a number of videos. And the idea would be to get the essence of it, not to get into the nitty-gritty of a particular example that I'll show you. Not to say, oh, there is this guy who is waving his hand, and why is he waving his hand? Not to that nitty-gritty, something that, a coarse-grained view of the phenomena that I'll show. Okay, so let's begin. So which one is closer? I guess this one. Okay, so synchronization, it started with this there's a pointer. I guess this one is a pointer, or does it work, or you don't see anything? Maybe this one. Okay, it doesn't work. Either of these two, no? Or maybe it is switched off. Okay. Okay. So in the meantime, I just go on. Okay. So it all started with an experiment done by Christian Huygens, this Dutch physicist. In maybe I just come down here, who in 1665 had just invented the pendulum clocks. The pendulum clocks that you perhaps are not familiar with. You haven't seen. How many of you have seen pendulum clocks? Oh, quite a. I was thinking that the number would be even fewer than. Okay. Anyways. So pendulum clocks are basically sticks that you hang from some support, and then you let them go, and then it exhibits some periodic motion in time. And it was invented by this Dutch physicist in 1665, and he was not well, he was bedridden, and he was writing a letter to his father. Not email, of course, a letter in which he mentions about this, talks about this particular experiment. Okay, yeah. Okay, I should do that. Yeah, okay, yeah. Okay, I had forgotten. Yeah. Okay. Oh, gosh. No, the pointer still doesn't work. No.
You go with this.
No, but the pointer is not.
It should be working. No.
Maybe I use my hand. Stick, you have a stick?
Maybe it's just a backup. I'm sorry, hold on
Okay,
just a second.
okay, maybe this one is what, okay, some complicated thing. Okay, let me just go on, until he comes back. Okay, so these are two pendula. They are suspended from the same support. Okay, so this is the common support. And he mentions that it is quite worth noting that when we suspended two clocks meaning two pendula from a common support, then the motions of each pendula in opposite swings were so much in agreement that they never receded the least bit. What he meant is the following, that he gave a kick to this guy, and then let them just go, continue with their own motion. And after a certain amount of time has passed, he finds that independent of the initial kick that he has given to these two pendula, they start doing swinging motion at the same frequency and amplitude. Okay. So this was the first documented observation of synchronization. In fact, what he mentions is some video here. Okay, so these are kind of a caricature of what Christian Huygens had seen. I mean, these are two pendulum clocks. Of course, they seem to be hanging in air, but they are supported by the common beam that I showed in the experiment. And here you see that the two pendula, they are exhibiting in phase synchrony. That the phase is there's a constant phase difference between them, and then the phase difference is actually zero. I mean, between the two. And this what you would call anti-phase synchrony. If one guy is going to the left, the other one is going to the right. And they are doing it in perfect synchrony. And the last one, of course, would mean that there is no synchrony in the system. And of course, I mean, this is an example of a physical phenomenon that is quite common in nature. So I'll show you, I'll flash some videos. They are all available on YouTube. So the first one has to do with metronomes. Now, how many of you have seen metronomes? Quite a few, especially those who, I would say, play some musical instrument. I mean, metronomes are used to tune music. Now, of course, you have apps and all, but in earlier days, people used to use the metronomes for tuning their musical instruments. So what you have is that you have a metronome. What you can do is that you can tune it to a particular frequency. And so what I have is that in this experiment, you have several such metronomes. Each one of them has got its own frequency. Okay, you have somehow tuned it to its natural frequency, and there are 4 such metronomes, each one having its own natural frequency, and you keep it on a common platform. Okay, why do I need this common platform? That will be evident in a minute. Maybe I'll just ask you, but let's first see the experiment. So the experiment is the following. I hope the sound plays. The sound doesn't play. Yeah, it does play. But is it too low, I guess, no? Is there a way to make it? Probably not. Can you hear something? Probably not. Unfortunately, it would have been nice if you... Maybe this is a way to check how attentive you are. So let me just go back. Okay, let me just go back and play the video, and let's see how attentive you are, and you will find that something is happening as time goes by. You see, what the guy is doing is he's setting each one to a different initial condition. So you see, now they are all oscillating at the same frequency. So you just hear one sound instead of 5 different sounds. Okay, this is one example. The second one, thankfully, doesn't have any music. So it's the example of fireflies. So fireflies are insects that you find in Southeast Asia, and especially the male fireflies. They have this thing that they want to attract the females, and the way they do it is that they gather on trees and they flash light. But then they flash light in a particular manner, in the sense that what happens is that you have a swarm of these fireflies gathered on trees, and each one of them is capable of flashing light at its own frequency. But once in a while, what happens is that there's this large collection of fireflies. They tend to come to synchrony and flash together. So you suddenly see this bursts of light flashes on and off. So like what you see here. You see that there are these sudden flashes of light that you see spanning across the whole of the screen. Okay, I hope you can see that. Okay, although each one is capable of doing its own dynamics, its own frequency of each one has got its own frequency of sending out the signal. Yes, yet they do something like they adapt themselves somehow to a common environment such that they flash this thing. By the way, one thing I forgot to ask you, which is that common to Hagen's experiment and this metronome is this platform, okay? And can you tell me what does this platform do? Like, is it essential for this platform to have all these guys coming to synchrony? And if it is so, then why it is essential? What does the platform do? Absolutely, absolutely. So what this platform does is that it lets the metronomes talk to each other. So bring about some interaction between them. Okay, and it's a weak interaction. It's weak because it's placed on this. Of course, I could not have placed this guy on a wooden table because then it would be very difficult to transmit the information. So that's why they have been placed on these cans. But it's not a very strong interaction. I mean, it's not that this guy is one of the metronomes is forcing the other one to absolutely come to synchrony, and yet they come to synchrony. We will see that this is the recurring thing, that weak interaction, etc. There is another example. I guess this one also doesn't have some music. So this is the example of a beating heart, and this is the reason why we are here. What we have is that in our heart we have these cardiac cells, and there are millions and billions of these cardiac cells, and what they do is that each one is capable of sending out electrical signals, and these are the signals that you record when you do ECG, electrocardiogram, etc. Okay? When somebody gets a heart attack, these things don't go very well, and what happens is that each of these cardiac cells is able to send out some electrical signal, but then they come in synchrony. I mean, the signals are all synchronized with one another, so much so that this cumulative effect of a large number of electrical signals is able to compress and expand the heart to the extent that the heart is capable of pumping blood, and to the extent that it can do its own function. Okay? So this is another example of synchrony. This is a nice video of flocking birds. Those of you who work in active matter and active matter maybe. So these are birds, like swarm of birds, and you see this very nice structure of collective effect, that they come to synchrony in some way, that there are these nice patterns, that this is not a computer simulation. This is actually what nature exhibits. You find these very nice features of patterns forming and going around and so on. And I guess the last example is that of clapping audience, but this one has again some audio. So the example is the following, that when you go to a concert and so on, and let's say the concert has been quite good and you want to applaud the performer. So the way it happens is that you, of course, you would clap, and everyone has got the freedom to clap at his or her own frequency and so on. But what happens is that spontaneously, what happens is you must have encountered it, or perhaps you should make a note of it next time you are in a concert hall. Now what happens is that after some time, although you try to clap at your own frequency, suddenly you see that the whole collection of people who are gathered, all the people who are there, they tend to clap together. Okay, so let me just play the video. So there's no synchrony now. Now there's synchrony. And of course it would die out. Of course you don't want to remain in synchrony all your life. At some point you have to go home and do other things. Okay? So the main thing to note is that here you see nobody is forcing another person, nearest neighbor or next nearest neighbor, to behave in a particular manner. Okay? And you are also not, when you clap, you don't quite clap, you want to emulate the next guy, and therefore you would like to clap according to him and so on. Nothing, you don't do like that. Your system somehow spontaneously adapts to this common environment. You hear some common sound, and unconsciously or consciously maybe you try to adapt to it, and therefore you end up clapping at a common frequency. So in all these examples, so there are two key ingredients. So the first one is, what are known as self-sustained oscillations and oscillators. So what do I mean by that? What I mean is the following, that to have synchrony, what I need to have is, of course, I need to have these constituent elements, like, okay, I have a collection, so I have to say what does each guy in this collection do, or what is it capable of doing. And so each guy is capable, each constituent element is capable of exhibiting some oscillation, but these are self-sustained oscillations in the sense that each unit has got its own source of energy, and therefore each unit is capable to exhibit oscillations. So these are self-sustained. Self-sustained meaning that there is no driving force or anything that is forcing the unit, each unit, to oscillate at a frequency, at some frequency. So these are self-sustained oscillators, that's one. Secondly, these oscillations, and we will reveal more of these features as we go along, these oscillations of these individual elements, they have a feature, namely that the frequency and the amplitude of oscillation that each guy exhibits is independent of the initial condition. The dynamics is such that we will see that this is very much unlike the simple harmonic oscillator motion that you all are familiar with. So each one is, for example, think of the clapping audience. When you clap, you have your source of energy, you burn your ATP, and you get some energy with which you are clapping. So you are able to clap at a particular frequency, and that frequency is independent of the initial conditions. Typically, we all clap, we all have our own characteristic frequency. Some people would clap by holding the hands this way, some people do it this way, or whatever. So, and these are self-sustained. So in dynamical system sense, what you have is this sort of thing. So this is what is known as phase space. We will learn about it later. So this is the position and the velocity of a particle. And what I am showing is the trajectory, the dynamical trajectory of the particle in this position velocity space, starting from two different initial conditions. So this is one initial condition, and the red dot is another initial condition. And what you will find is that independent of the initial condition, they eventually, in the long time limit, both of them go to a periodic orbit, which is of course independent of the initial condition. That is to say that in the long time limit, the system will exhibit oscillations that have a characteristic frequency and a characteristic amplitude independent of the initial condition. And the periodic orbit that you eventually get to is what is shown on the right. So let me just play the video. Yeah. So you see that here, both the red and the green dots, they eventually, like asymptotically, they approach a closed orbit, and the closed orbit is shown there. And you can play with like other initial conditions also. And we will see that this sort of dynamics are very much typical of nonlinear dynamical systems. You cannot have a simple harmonic oscillator in which such a thing happens. Okay, these are linear systems. So these are for the individual elements. Okay, so I have many such elements, and the second ingredient that I need is second ingredient that I need is I need to have some interaction between them, because what I want is I want many such elements. Each one of them has got its own frequency and amplitude of oscillation, and I put them in contact with one another, not in contact really, interacting with one another, but the interaction has to be weak. Why does the interaction, why does it need to be weak? What about a strong interaction? Absolutely. Yes, absolutely. That if the interaction is very strong, then there is no surprise in having this effect. You get this effect despite the fact that the interaction is weak. So that's the surprising part of it, that I put these metronomes on a common platform, which is some wooden block or something. So the interaction between the different metronomes is rather weak, because what each metronome has to do has to set into motion the atoms and molecules constituting the common wooden block, and it's a very weak interaction, and yet you get synchrony. Had it been strong interaction, then there is no, and first of all, if you really had strong interaction, then probably you would not have been able to distinguish between the different oscillators. There's just one big chunk, okay, made up of many. But here the interaction is weak, so therefore there are all these elements. Each one tries to go his or her independent way, And there's some interaction which is very weak. Think of the clapping audience. Nobody is putting you on gunpoint saying that, yeah, you have to clap at this frequency. Nothing of that sort. Yet you end up clapping at that frequency. So that's a part of it. That makes it interesting. So what we will do is we will, of course, as a theoretical physicist, we will learn to address, how can such a thing, like emerge in a many-body interacting systems. And we will address this question both in classical and quantum setting. We will understand what do I mean by classical synchronization, what do I mean by quantum synchronization, 1 minute. And then we will see how to address them. And I'll tell you the plan of lectures that I have in mind. But before I go on, let me just, I'll take your question in a minute. So this is a model system in which people could do analytical calculation to show how, despite having weak interaction, you may have synchronization in a system. And this model was invented by Kuramoto. Let me first play the video to see how does it look like. So here what I have done is that I have, these are the phases of the oscillators. As we will see, these oscillators, there are many oscillators. Each one can be characterized by a phase. Phase meaning an angle that goes from 0 to 2 pi. And here, what is happening is that as time goes by, each one is going around with its own frequency. So there is no synchrony in the system in this case. And there is absolute synchrony in the other case. This is the, what is K? K is the coupling. K is the strength of interaction. If the strength of interaction is large, then you see that there is synchrony in the sense that the phases are evolving in time, but the difference between the different phases is a constant that is independent of time. This is what you see when the system is synchronized, what you call phase locking. This is when the system is not synchronized, and this is somewhere in middle. This is the bifurcation point or the phase transition point. And this model was invented by Yoshiki Kuramoto. It was considered a big breakthrough in nonlinear physics. He did it in, I think, 1984, around 1984. And the good thing is that this year he was awarded the Boltzmann Medal. I don't know how many of you would know about this Boltzmann Medal. This Boltzmann Medal is awarded by the C3 Commission of the International Union of Pure and Applied Physics. And this is considered the highest honor in nonlinear and statistical physics. And the highest honor to the extent that the rule is that if you have been awarded a Nobel Prize, you would not get the Boltzmann Medal. Perhaps you don't even care, but anyways, I mean, that's a rule. Okay? But it has so happened that many people who won the Boltzmann Medal went on to win Nobel Prize. So there are 3 such people. So the first Boltzmann medalist was Ken Wilson, the father of renormalization group. He was the first one to win the Boltzmann Medal, and of course he went on to win the Nobel Prize, I guess in the same year. The next name that comes to my mind is Giorgio Parisi. Parisi was given Boltzmann Medal way back in, I think, late 90s, and he was given the Nobel Prize just a year or maybe 2 years ago. And last year, the Boltzmann Medal was given to John Hopfield, and he was also, awarded the Nobel Prize. So I don't know what fate has in store for Kuramoto, but we'll see what. Yeah, you have a question.
Yes, sorry, you mentioned weak interaction.
Huh.
In the first case, we have like global coupling interaction.
Yeah.
But in the other cases, such as the butterflies,
Yeah.
it's a local pairwise interaction. So it's like what precise kind of interaction?
Yeah, that's a very good question. So I'll come to that. I'll mention what sort of interaction you need. Of course, global is the ideal one, because if you, if we are able to sense the global, ambience, then of course it's easier to synchronize. Local would be more difficult because you would then tend to synchronize to the local guys, and there could be many different clusters. I'll come to that when I come to the models and so on. But you see, when you are clapping, you may think that there is no global thing, but actually there is one, because your ear is not able to distinguish so much between, maybe you hear a little bit what the next guy is doing, but if you do it unconsciously, then you tend to hear a global noise or something. So in that sense, it is kind of global, but I'll come to that, what sort of interactions you need. Weak doesn't at all specify fully the nature of interaction. You have to tell me how does it decay with space and so on. Okay. So this is what I plan to do, what you will learn in this course. What I'll do is that, of course, you will learn about classical and quantum synchronization, the phenomena, what does it mean to have classical synchronization in classical systems and in quantum systems, and the tools of analysis. But along the way, we will use synchronization as a template to learn several topics in these three branches. These are kind of foundational subjects in physics, theoretical physics at least, nonlinear dynamics, statistical physics, and quantum dynamics. So in nonlinear dynamics, we will learn about what do you mean by fixed points, limit cycles, phase approximation, multi-time scaling, and bifurcation. Each one of them is a topic in its own right, but then of course we will touch upon, we'll scratch the surface and find out what is it all about. And then I have ample exercises to keep you busy and not to get distracted by the lovely weather that you see outside. It's your choice whether you want to synchronize with the exercises or with the weather. So the next one is statistical physics. Of course, we will use this synchronization as again a framework to learn about equilibrium and non-equilibrium statistical physics. We will try to understand what do I mean when I say that a system has an equilibrium stationary state and what it means to have a non-equilibrium stationary state. And then we will along the way learn about such tools of analysis as Langevin and Fokker-Planck equations. And then towards the end, we will talk about this very exciting topic of which Edgar is a local expert. I mean, so if I do some mistake, you have to catch him and not me for maybe the papers were written very well. So you have to catch him and not me. So this is the subject of stochastic thermodynamics. So this is thermodynamics the way we know, traditional thermodynamics. But then these are applied to small systems which are comprised by, let's say, one or a few degrees of freedom. And how do the laws of thermodynamics generalize when you have small systems where fluctuations are dominant. And then there are some universal theorems called fluctuation theorems. So we will see how we can use synchronization as a way to learn about this stochastic thermodynamics. And towards the end, I plan to spend some 3 lectures on quantum dynamics, and especially to learn about open and closed quantum systems and what are known as Lindblad equations. This part is a bit heavy. So it depends on your preparation, like how much you know about quantum systems and so on. But what I have done is that in my lecture notes, which I'll eventually circulate and put up on the website, I have given ample derivations of, or at least, we will recall some basic results in quantum mechanics. So we learn about Lindblad equations and something known as Wigner function, and then, quantum harmonic oscillators and coherent states. So this is, so just to get an idea of where do we stand, or where do I stand in terms of, preparation, your preparation. Can you tell me of these topics that I mentioned? Let's see, how many of you are not familiar with, because that's probably the easiest question to answer. Not familiar with these topics, limit cycles, multi-time scaling, bifurcation, etc. You aren't familiar with, okay. So the rest, so then this makes my life really easy. How many of you aren't familiar with equilibrium, non-equilibrium, and fluctuation theorems and stochastic thermodynamics? You all know about them. Okay. And what about the quantum part? Okay, great. So basically, no, you are not familiar with, right? That's a question that I had put. Oh, you are not familiar with the quantum dynamics. Okay, so then instead of spending, so Edgar and I, we were discussing, so we were thinking that we will devote 1 lecture to quantum dynamics, but then it seems like I should devote the whole series of lectures to quantum dynamics. Huh? So tell me, like, what should I do? Like, should I maybe take the first lecture as kind of a way to, make you understand what pace I'm going and so on, and then decide like how much time should I spend on these two, because this is really like the difficult stuff and it requires a lot of calculation and so on. What do I do? How do you want me to do it? Like, should I gloss over these things very quickly, or you want to take a decision after I have given 1 lecture? After you have given. I guess there is some synchrony in that answer, I guess, most of you. Yeah.
I don't understand if your plan is to revise, theoretically, these kind of topics, or see how this relates to.
No. So I don't want to, of course, revise these things. What I want to do is that I want to see how these things emerge in the setting of synchronization.
Because, like, even though, for example, even though I am familiar with the statistical physics part, I would like to understand how it relates.
Indeed. So the idea is, as I mentioned here, we will use synchronization as a template. So we will see how synchronization allows you to apply these concepts. Not to give an introduction to fluctuation theorems and so on, because that would be, I will be, I mean, that would be like impossible to do. I've stated some references. So for synchronization, I guess the first book is the Bible, so or whatever is your holy book, the equivalent of it. This has everything that you want to know about synchronization, but this book is a bit outdated. It was written in 2003, and I don't think it has come up with a revised version. This is the second book is the original book by Kuramoto, in which he talks about chemical oscillations and so on. So you may be tempted to feel that the second book is probably a bit light given the title, chemical oscillations, but actually it's very heavy, very difficult to read, because these are people coming from maths background and dynamical physicists, so not easy to read. While the third is highly recommended, like it gives a very, very nice introduction to synchronization. By Strogatz, Steve Strogatz. Perhaps you all know the name because he has a very popular lecture course on nonlinear dynamics that you find on YouTube. And this one gives a very, very, very nice introduction to synchronization and its connection to kinetic theory, Landau damping, etc., etc. This is a review on synchronization that you can find, Felix Ritott and others. We incidentally wrote 2 reviews. So these are a review and a book. So this one is a bit recent, 2014, maybe 10, 11 years ago. And this is a book. And the last one is a book that doesn't necessarily talk about synchronization, but there are many topics that it does deal with that will have overlap with what I will talk about in these lectures. Okay? So I think that's the plan. So let me just start formally the lectures, I guess. So like any questions before I move on? So quantum dynamics, since you want to learn about it, so tell me, like, do I take it for granted that for quantum harmonic oscillator, of course you know about the ladder operator. So how many of you aren't familiar with ladder operators? You all are, and creation, annihilation operators and so on, these you aren't familiar with. Okay. So this I would recommend that in the notes I have added an appendix where you will find some basic formula and you have to just work them out, because it's basically some very basic quantum mechanics stuff. So how many of you aren't familiar with coherent states? So there's something called coherent states. Okay, so majority of you are familiar with coherent states, and Lindblad and Wigner, Lindblad equation. Okay, so quite a good number you don't know about Lindblad. I mean, it's okay. I also didn't know about it at some point. And Wigner? Wigner also has a good number. Okay, so really quantum is going to keep me busy. Okay, fine. So are there questions? Sorry, yeah. I don't? You don't understand why? Oh, this is the quantum year. No, they are giving you money to do quantum. Maybe that's the simplest answer, best answer. But you see, you would also like to see when you see that's the honest answer, and the dishonest answer, or maybe another answer, is the following: that you see a phenomenon happening in classical domain when you are dealing with a glass of water, something macroscopic that you see with your eyes, and probably it's a human curiosity to ask, how do these things apply when you make the glass of water smaller and smaller? when you no longer have the Newton's equations and the equations of motion are no longer described in terms of the positions and momenta, but in terms of wave functions, and you have an extra element of uncertainty, which is quantum fluctuations. I mean, in classically, the glass is here, the glass is here. That's the end of it. So therefore, the metronome is there, the metronome is there. That's the end of it. But quantum metronomes can be here and there and so on. So you would like to see how do the classical laws get modified, or how does one even talk about synchronization in the quantum setting. So in that sense, that's a general. You do something classical and you want to see if at all there is an equivalent quantum answer. Okay? Okay, so shall Okay, so I will come to that. So I haven't even, in fact, there is an assignment problem in which I talk about, I have given one problem that you need to work out. So simplest answer is the synchronization. It's a very non-linear phenomenon. It doesn't have to do with, it doesn't occur in linear systems. So let me just get going, because that will probably answer the, so before I go to non-linear oscillators and so on, so let's just quickly recap linear systems, okay, or let's say linear oscillators. So since you all know about these things, I will be fast. So the linear oscillators is, of course, the one that you all know about. It's a simple harmonic oscillator where x and p are the coordinate and the momentum of the particle, and the equations of motion are simply the Hamilton equations. X dot is equal to del h del p, which is p by m, and p dot is equal to minus del h del x, which is equal to minus m omega naught square x. Dot means I am taking a derivative with respect to time, and you can combine these two into a single equation, x double dot plus omega square x equal to 0. So this is a simple enough equation to solve. So if you solve it, you get an answer which is of the following sort, subject to some initial condition. So what is this x naught? It is just the initial coordinate, and v naught is the initial velocity. Okay. So at once you see that a simple harmonic oscillator is not going to qualify as a constituent element of a synchronizing system, simply because the position of the particle at a later instant given an initial condition is explicitly dependent on the initial condition. See, we want elements that would exhibit oscillations that are generic to those elements, in the sense that whatever be the initial condition, typical initial condition you endow the system with, it would eventually in the long time limit exhibit oscillations that do not have an explicit dependence on initial condition. So this is not going to work out. So simple harmonic oscillator is not the right element to talk about. And in fact, there is a better way to understand it, which is you recall the picture that I had shown in the position velocity space. So let me come to this notion of what is known as a phase space. Like again, you must be familiar with it. So phase space, it's a space spanned by the dynamical variables of the system. Dynamical variables are variables whose values are changing as a function of time. For example, for a harmonic oscillator, the dynamical variables are the position and the momenta. So here you put your position and here you put your momenta, and then starting from some initial condition, you basically draw how does the point trace out a curve or a trajectory in this phase space. For the simple harmonic oscillator, it is quite easy to write down or draw the corresponding trajectory by making the following observation, that if I look at the time variation of the energy, or how does the energy change as a function of time, of course I will get 0 because this is a Hamiltonian system. So therefore energy is a constant of motion. That means if I start with an initial point x0 and p0 that has got some energy E0, then of course as the point traces out a curve in this trajectory, the energy is going to remain constant in time. X and p can change, but the energy cannot change, and therefore I can rewrite this equation in the following way. That would give me the equation of this will give me the equation of an ellipse 2 by m omega square E0 equal to 1. Okay? If I just rewrite, because energy is a constant of motion, and let's say I start with an energy E0, so therefore in this phase space I am going to get a, doesn't look quite an ellipse, but I guess you can live with it. Okay? And in the assignment problem, I have given a simple exercise to show that the direction this ellipse is traversed is this clockwise direction. This you can easily figure out. So of course, if I give one value of energy, you get one ellipse, and if I give you a different value of energy, you will get a different ellipse. Okay, so let's say this is E0, this one corresponds to E1, and so on. I am not saying that these are energy levels. This is simply not possible, simply because all x and p values are allowed. So therefore, you are going to get an infinite number of such ellipses. I mean, this region is completely filled with ellipses, one after the another. There is no gap. I am just saying that E1 is greater than E0, something like that. But now I make an interesting observation, which is the following: that suppose you are on this, on this trajectory at this point. Okay, so you have a certain x value and a certain p value, and suddenly you give some energy to the system. Okay, what you do is that, let's say you perturb the position of the particle, or you change the momentum of the particle, or you do both. And in doing so, suppose the energy of the system increases. So let's say you go from the energy value E0 to some energy value. Then what the system would do is that the system would at once jump to a new orbit corresponding to this new value of the energy. Okay? And there is no possibility for the system to come back to its initial orbit. Okay? So as you keep perturbing the system will go only in the forward direction, like it will jump from this orbit to this, to this, to this, and so on. But there is no mechanism in the dynamics that would bring it back to the trajectory that I started out with. And this is quite unlike the phase space portrait that I had shown in the video, where you found that regardless of all initial conditions, you eventually approach a master kind of a closed trajectory. This is not going to happen here. And this is all these things, these are manifestations of the fact that this system is linear, in the sense that when I write down the equations of motion, this equation is linear in momentum and this equation is linear in x. So being a linear system, what happens is that if I consider one independent solution x1t and I multiply it by an arbitrary constant, I take another initial condition and I multiply it by this, this is also a valid solution of the equations of motion. And being linear, what happens is that this is what is going to happen, that you are on one orbit and then you give some kick, it will jump onto another orbit. There is no mechanism in it to bring it back. Okay? I have given some exercises to see what happens if you introduce damping in the system. If you, for example, instead of studying the simple harmonic oscillator the way I have written, suppose you do this, x double dot plus omega square x plus gamma x dot. If you bring in some dissipation in the system where, let's say, gamma is positive, then also you can work out the solution exactly. Then what is going to happen is that here x of t at long times would just oscillate as a function of time. If I plot it as a function of time x of t, it would just oscillate. Maybe it starts from x0. So, okay, let's say x0 equal to 0 for this plot. Okay. Here what would happen is that if you introduce damping, then x of t as a function of time would do what? It would oscillate and eventually decay and go to 0. So this is also this is also something that you don't want. You don't want the metronome to just stop oscillating. Then there is no question of synchronization among many metronomes put together. Okay. What about introducing a periodic forcing? Okay. If you do this, then of course what will happen is that what this periodic forcing would do is that it would kind of pump up this thing, that if the what the dissipation does is that it tries to kill all oscillations, and you counter it by pumping the system, pumping some energy into the system with the help of an external drive, and then of course it would go to non-zero value of x of t at long times. So this also you probably know, that x of t at long times, depending on the values of the different frequencies, the capital omega, which is the driving frequency, and the natural frequency, what it would do is that it would like eventually go to some non-zero value, and it would settle to some non-zero value. Okay, and that non-zero value would depend on the amplitude, and it would depend on the square, the difference of the square of this guy, and so on. Okay, and then if you have resonance, that is to say that if these two frequencies coincide, then you find large oscillations and so on. But like again, this is not what would constitute a synchronizing element, because here what you are doing is that you are imposing oscillations in the system with the help of an external drive. So this is not a self-sustained system, in the sense that you are including a source of energy, you are allowing an external force to keep the system oscillating in time. This is not what I want. I want a system that can sustain oscillation on its own. There should be a mechanism in the dynamics that doesn't require introduction of an external driving force to do the job. And this brings us to the notion of nonlinear oscillators. As the name suggests, nonlinear oscillators are oscillators whose equations of motion won't be linear, but they would be nonlinear in time. So what I would do is I start with the equation of motion of a harmonic oscillator and see how I can make it nonlinear. And of course there are 10,000 different ways to make it nonlinear, but one of the representative ways to make it nonlinear is the following way. That you see, this was the equation of motion of a linear oscillator. This equal to 0, I keep some space here, okay? And we found that if you introduce, let me for a moment change notation, so gamma now becomes mu, I'll explain what it is. So let's say mu is larger than 0. So we just saw that if you have a damping term, then this doesn't do the job, in the sense that x eventually in the long time limit would go to 0, okay? So what you do is that you make this dissipation term nonlinear. Okay? So this is nonlinear in the sense that, of course, I mean, this is linear, but here you see there's an x cube, so this makes it nonlinear. Let me just see if I write x square minus 1 minute. Okay, fine. Mu is still positive, but now you see what's a new thing that is happening. Let's look at this equation. You see this equation, this will change sign depending on the value of x square with respect to 1. Suppose x becomes very large, so large that x square is larger than 1. That is to say, I start from some initial condition, I let the dynamics go in time, and let's say at some instant of time, x becomes larger, x square becomes larger than 1. So if x square becomes larger than 1, this term looks like a positive quantity, it behaves like a usual damping term. So this will then try to bring down the value of x. Just as what happens if you have a harmonic oscillator, x double dot plus omega square x plus gamma x dot equal to 0. If gamma is positive, then it would not allow x to grow indefinitely in time, it would just try to bring the value of x to smaller values. So therefore, if x square becomes larger than 1, then what you have is you have positive damping, and therefore what it would do is that it would bring down the value of x. But then does it go all the way down to 0? No, because at some point what will happen is that if it becomes smaller than 1, then the sign of this term becomes negative. And if it becomes negative, then it is no longer positive damping, it is negative damping. So it would pump it up. So if it becomes too large, it pumps it down. If it becomes too small, it pumps it up. Okay? So if x square is smaller than 1, then you have negative damping. And so what it would do is that it would pump up the value of x. So as you can imagine, there are these two effects which are kind of countering each other's influence. One is trying to make the amplitude too small, the other is trying to make the amplitude too large. And so there will be a balance between the two that will be attained in the long time limit, and therefore in the long time limit you may expect to get a value of x which corresponds to a balance between these two countering effects, and that would we will see that in fact defines a limit cycle, namely the closed orbit that I showed in the simulation, namely a trajectory in the phase space that is independent of the initial condition, that has got its own natural frequency and an amplitude. Okay? So this oscillator, it is very popular and very famous in the nonlinear dynamics literature. It is called the van der Pol oscillator. I think van der Pol was working in the Bell Labs when he came up with this in the context of vacuum tubes and so on. So, so this is what it is. Okay. Now, how do I show whatever I talked about that if x square becomes too small, then it pumps it up. If x square becomes too large, then it pumps it down, and therefore it goes to a limit cycle. All these things, how do I show? The problem is that this is a nonlinear equation. And as the first thing that we note is that being a nonlinear equation, of course, you can write it as two coupled first order differential equations, just as the way we had done it for the simple harmonic oscillator. So what you do is that you define two quantities, x1 and x2, where let me just see, x1 is the position and x2 is the velocity, let's say. So these are the defining equations, and then these equations would boil down to a set of coupled differential equations, first order in time. dx1 dt is equal to x2, and dx2 dt is equal to mu of x2 1 minus x1 square minus x1. So these are, okay, these two systems are absolutely equivalent. Here also you need two initial conditions to solve for the dynamics, x of t as a function of time. Here also you need two initial conditions. But the thing is that these are nonlinear equations. So if I look at the right hand side, this one is linear, but the second one is highly nonlinear. So the first thing that doesn't work is the linear superposition principle doesn't work, that if I find two independent solutions of this equation and then I multiply each one of them by an arbitrary constant, then that superposition is no longer a solution. That doesn't work. That's one. Secondly, you cannot really talk about energy of this system because, of course, there is a damping term that doesn't allow these equations to be written down as Hamilton equations, but also because of this strange form of nonlinearity, you cannot really write down as some Hamilton equations in presence of some damping and so on. Okay? Because damping, let's say, since you are familiar with Langevin equations, you always have a damping which is of the form gamma x dot. You never have a nonlinear damping of this sort. So then how do I demonstrate whatever I claim to be true? So of course the first thing to do is to do some numerical integration, some simulation. So let me see if I can bring this up. So you can do it on, okay, maybe I have this one. Okay, does it work? Okay, so here I will share this code. It is written by one of my students. So what you are doing is that this axis is position and this is velocity. So wherever you click, that is going to be your initial condition. Okay, so you eventually get a trajectory. Okay, and what you see is that you click from some other initial condition, keeping the value of mu fixed. Let's say you change the initial condition, and you will find that you go to the same trajectory, same long time solution, which is in the form of this slightly distorted rectangle. You start from here and you see that you go there. Same long time solution. Start from here, you go to the same solution. Okay. So this is exactly what you need. What you need is a long time solution that is independent of where you click on. You click on here, you go there. You click on here, you go there. And you seem to be going to a closed trajectory. Okay. Because this is a closed trajectory, you seem not to see any motion after t hits a particular value. That's because you keep repeating the same trajectory. So you have a periodic orbit that is independent of the initial condition. So this is what is known as a limit cycle, and we will see that in two particular limits of this van der Pol system, you can solve for the limit cycle exactly, and then we will see what sort of equations of motion describe the motion along a limit cycle. So you all are familiar with limit cycle, that's what I understood. So do you know how does one solve this van der Pol equation in these two limits? So one limit is this mu much smaller than 1. This is the weak nonlinearity, because this term multiplies the nonlinear factor here. So this is the weak nonlinearity limit, in which you can solve for the long time solution using what is known as the multi-time scaling analysis, which is very standard in nonlinear dynamics. So in this case, you can find the form of the trajectory, and the second one is what is known as the relaxation oscillator limit, where mu is much larger than 1. That is, you have a very strong nonlinearity in the dynamics, and this, what you get is relaxation oscillations. So do you want me to go over them, or you know about them? Then the system is? Yeah, it is bounded, because you see the system is bounded simply because of this condition. It cannot go really outside this, if you go out, you eventually come back, and if you are too much in, you are eventually pushed out. In fact, in the assignment, I have given up an exercise to show if you draw the phase portrait of this system, x1, x2, you will find that 0, I'm considering the case, I guess it will be true for all mu. Mu can be anything positive or negative. So this is a fixed point, and you will see that this one becomes unstable. So you eventually go out to a limit cycle, and that takes place for every value of mu. It is only that when mu is very small or very large that you are able to obtain an analytical solution. Otherwise, it is not possible. You have to just do some numerics and perturbation. Also, to have some perturbation done for this system, you have to have a small parameter. So when mu is very small, mu itself is the small parameter. When mu is very large, 1 by mu is a small parameter. You want me to do that, or I just skip? Let's go over, you said. Okay. Like again, this is what most of you want, or? Okay. Let's see. At least I do one of it. one of these two things. Maybe I'll do this mu larger than 1, this one, and this mu smaller than 1. I have already worked out full details in the notes, and I've also assigned a problem. So what you can do is that you can go through the notes, learn about the technique, and try to apply it to a different problem, a problem different from Van der Pol oscillator, to see if you understand the technique. Okay, that's a fair deal, right? Okay, fine. So let's talk about this mu much larger than 1 case. And what happens if mu is negative? Then also eventually you go to element cycle, but then the features that you find when mu is smaller than 1, that also I have assigned as a problem. So somehow problem, the word itself sounds very daunting. It seems like it is unsurmountable, but actually it is not so. So therefore don't be scared if I say this thing, okay? So when mu is much smaller, when mu is much larger than 1, somehow I have to invoke some time scale separation, something would tell me that these are the processes which are dominant in this time regime, and these are the processes which are dominant in that time regime, and so on. So I completely concur with what my previous lecturer Ariel was mentioning, that it is very important to have first the idea, and then you have to write down, express them in terms of equations. So the idea here is that if mu is much smaller than 1, then a natural small parameter will be 1 over mu. So I have to somehow bring in this 1 over mu here in this equations of motion, and then somehow bring in a time scale separation. We will see that when mu is much larger than 1, then there are certain processes which are dominant in, let's say, over a time scale of milliseconds, and there are certain others which are dominant over time scales of 1 hour. And so therefore, if I wait for long enough, I am interested in the long time dynamics. So the fast dynamics, the dynamics that takes place over short time scales, would have happened so many times over that long time limit that I may just replace it by some average effect, while the slow ones are yet to happen, and these are the ones that are going to eventually dictate for me the long time dynamics. So that's basically the framework. Okay? So this is done in a very clever way. As you can imagine, like on the face of it, this doesn't look solvable, and of course you cannot do anything. So the first thing to do is to realize that this term, just this term, without the omega square x term, just x double dot of the first and the second term, that you can write as a total time derivative of this guy. So this is just algebra, nothing, it's just an observation. It doesn't solve the problem, it doesn't make my life simple, but I still do it. Okay, because you just to differentiate, you really get this one. So therefore, let me now introduce two functions, f of x. It is just for convenience of notation. Let me call this guy to be f of x, so which is x cubed by 3 minus x. I just don't want to keep writing these things, and I define another function w of x. As you can guess, w of x is this whole thing. Okay, this whole thing is w of x. So w of x will be what? It would be x dot plus mu times f of x. Okay, nothing great deal. This is just simple mathematics. But then I find that if I now want to write down what is dx dt, so what is x dot? Okay, because writing x dot. So you see, x dot plus f of x is w of x, right? Because this whole guy I am calling it w of x, and this bit I am calling it f of x. So I know that x dot plus mu f, okay, it's written here x dot plus mu f of x is w of x, so I can just switch sign and write that x dot is nothing but w of x minus mu f x, no problem. But what about w dot of x? W dot. So what is w dot? W dot is this guy, you take the time derivative, x double dot plus mu, and then you take the derivative, you get what? If you do w dot, you will get x double dot plus mu x dot of x square minus 1. Right? If I just take the, just the time derivative, I'll get this. But x double dot plus mu x dot x square minus 1 is nothing but minus omega square x. Okay, I'm taking, just for simplicity, I'll take this omega to be 1 without loss of generality. Okay. So therefore, what I have ended up doing with this transformation is to replace this second order differential equation into two coupled first order differential equations in these two dynamical variables, x and w. These are now my dynamical variables, and the dynamics is such that x dot is equal to w minus mu f of x, and w dot is equal to minus x. Okay. You may say, oh, why did I not do x1 is equal to x and x2 equal to dx dt? I could have just written them down in terms of the position and the velocity. You will see why do I do it, okay, in a minute. Now you see this mu, the factor mu here, it's a gigantic number because we have decided to work in the limit in which mu is much, much larger than 1. So therefore, this second term, it is much, much larger than the first term. So therefore, let me do another transformation, which is the following. So what I want to do is that in order to have competition between these two, I have to have this w also to be very large. Okay, w also has to scale with mu, because otherwise this second term will dominate over the first term, so I may as well ignore the second term, first term. So therefore I need to consider large value of w. So what I do is that I define a new variable y, which is w by mu, which is to say that w is equal to mu y. If I write it this way, can somebody tell me what this quantity is of, like it is of order mu to the which power? You see what I'm trying to do? See, in this equation of motion, the second term is of order mu. So I want to make w also of order mu in order to have competition between these two terms. Otherwise, I'm not going to get anything interesting. So what I say is that in order to have this competition, this w has to be of order mu. So therefore, I define a new variable y, which is w by mu. And now I am asking, can you tell me what is the, this y quantity? This is of order mu to the what exponent? 0, right? It is because I have taken out the mu dependence there. Okay. So in terms of this y variable now, the equation of motion looks like this. Like again, you just substitute and you get x dot is equal to mu x times fx, x minus fx, which is w. I just mu y minus fx. Sorry, because w is mu y, so I just do that. And the second one is y dot is equal to minus x by mu. Yes, because I want to have a competition between these two terms. No, it's not an option which is valid. I'm saying that in order to have an interesting dynamics, I want to study, or let me put it this way. Mu is anyways very large. So therefore, I have to choose my w in the proper regime. Otherwise, there won't be any competition between these two. Mu I have already decided to be 10 to the power 576. And if I choose w to be 0.00001 and this is 10 to the power 576, I won't see any effect of W. It's as good as putting W equal to 0. Now you see, with this transformation, I have achieved whatever I wanted to. Namely, that now I see that x dot is a huge, gigantic number, because x dot, the velocity is changing in the x direction very fast, zap, because it multiplies, there's a multiplying factor mu. While y dot is a very sluggish guy, because it is divided by mu, so it doesn't want to change at all. Okay, very slow moving, and this is very fast. So therefore, I see that there is a time scale separation when I write down the or visualize the dynamics in the phase space in terms of x and y. You see, whenever you see a problem that has got let's say a parameter which is very large or very small, you have to somehow bring in some time scale separation, so that you can say that, let's say here x dot will change so fast, in that time y dot will almost not change. X dot will change very fast unless y minus fx is small. Yeah, because y minus fx can itself become 0, and then x dot will not change. So let's see how does the dynamics look like in the phase space. You are with me? How many of you are not with me? I always ask the negative question because I want some positive answer. So you are with me, right? I did not do anything. I did not even solve it. I am claiming to solve it, but I haven't done anything. It's just cheating and bringing in. Oh my goodness, I erased. But let me write it again. Yeah. How can I assume that mu x dot is constant? No, it's not constant. It is changing. No. If you differentiate, you get what? X square x dot minus 1, which is exactly what you have there. Na? X is changing as a function of time. So when you differentiate with respect to x, what do you get? So let me just do it. X cubed by 3 minus 1. If I do ddt of that, mu is of course a constant that I can happily take out. But ddx of x cubed by 3 will give me 3x square by 3 minus, 3x square by 3 x dot, sorry, there is an x here, minus x dot, right? Okay, and this I can write as mu of x square minus 1 x dot, which is exactly what was here. No, when I said I'm cheating, I'm not cheating to that extent. Then you would kill me. Na? Okay, so given this equation of motion, I started out with this equation of motion. Sorry, this omega I decided to put equal to 1. So mu x dot of x square minus 1 equal to 0, and then after those transformation, I had my equation written in terms of x and y, where x dot is equal to mu x minus fx, y dot is equal to minus x by mu, where f of x is this function x cubed by 3 minus 1, I guess, minus x. Okay. So now let's look at the dynamics in the phase space. So my phase space will be spanned by my two dynamical variables, which are now x and y. Okay. So this is my x, this is my y. Now one thing I note, that mu being very large, x dot is going to be very large, y dot is going to be very small, but this will be true provided x minus fx is large. If x minus fx becomes small or becomes equal to 0, then y dot will take over. So these are like two brothers, but this guy doesn't always remain the elder brother. Sometimes he changes sign. He becomes elder, and then he becomes, okay. So therefore x minus fx is going to play an important role. So let's just see what this fx guy looks like. So fx function is what? Fx function is x cubed by 3 minus x. So let's just plot this function. So it's a cubic function which is an odd function. I hope I drew it correctly. Not as Boltzmann had famously said, perfection is for tailors, not for physicists. So, but then I should be a little more perfect. Maybe this is slightly. At least you make out what it is. Okay, this is this function. You can find these points exactly. So this point is B. This is a minimum point. I mean, of a point. This is +1 minus 2 by 3. These are irrelevant, but I'm just saying that in principle you can find this point. This is D, whose coordinates are -1, 2 by 3. And then you can define two other points, which are like one point is this point A. Okay. This point has the same y value as the point D, but the x is different. You can just solve this equation to find what is the value of x. So this is 2 by 3. Again, these are not relevant. And similarly for this point D, I can define the corresponding point here, which is C, which has got the coordinates -2, -2 by 3. Okay? Fine. Okay? So I just drew this one. And let's start with some initial condition here. As I showed on that, with that like animation, I have to convince you that starting from any initial condition, I'm going to eventually get to an orbit that doesn't depend on the initial condition. So I start from some initial condition. Okay, this is quite far from this line. By the way, this line, this fx is x cubed by 3 minus x, and on this line x dot is equal to 0. Why? Because on that line x is equal to fx, so therefore x dot is equal to 0. So this line has a name, it is called null line. But again, you don't have to remember. But just that eventually if you see in the literature some paper that talks about it. Now let's start with this point, okay? Now you see from this point, it is very far from the null line, so therefore there is a huge gigantic x dot and a very small y dot that is going to make this point move almost, hit this point, come very close to it, almost horizontally. Why? Because x dot is very large, y dot is very small. Because x dot has a factor of mu here, y dot has a factor of 1 over mu here. So therefore, this, if I start from this initial condition, almost in no time it would come this way. Sorry, it doesn't come all the way here. It comes. And then when it comes close to this point, now what will happen is that now x dot starts to get smaller and smaller. Why? Because x is coming closer and closer to fx. Okay? So it zaps through, but then it comes close and then it slows down a little bit. And then eventually x dot becomes so small that now y dot becomes the elder brother. Initially x dot was the elder brother, so it just goes shh, and then it slows down a little bit because x dot becomes small, because x minus fx becomes small, and then y dot takes over. But what does y dot do? Y dot comes with a negative sign because I am in, so this is my origin, I am at like positive value of x, so y dot is going to make it go down. So what it does is that it comes here, it slows down, and the dynamics pulls it down, almost vertically. So it goes down, but at some point now, y dot again becomes smaller and x dot becomes larger. Why? Why x dot becomes larger? Because as it goes down, it starts to deviate, go away from this null line, so much so that now again mu minus fx will become large, and therefore x dot will take over. It becomes the elder brother. It takes over y dot, but now x dot has a negative sign. Why? Because now x is smaller than fx. You are, x is smaller than fx. You are on the other side. So therefore, you are pulled, you are pushed towards this null line. But then again, if it comes close, then again x dot becomes small and y dot pulls it down, and then does this and does this and does this and so on. It goes all the way until it comes here, somewhere close to this point. Okay. Once you are here, then of course again there is a gigantic x dot that would push it rather, in no time to come here. And again it will go up, and it would do like this, and it would come here, and then again it would do like this and so on. So there is a huge x dot velocity that makes it move when you are away from the null line. Then the y velocity doesn't matter, it's only the x velocity that is in action that pushes it very quickly towards the null line. Once you are close to the null line, it starts crawling. Because now what happens is that it goes this way, this way, this way, this way, kind of does this, goes away, then comes back, goes away, comes back, goes away, comes back. So it starts crawling, 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 and then at some point it comes here. Again, in no time it comes here, and it does this. Okay, and this just goes on. And as you make mu larger and larger, this motion, the horizontal motion, is almost taking place in no time. Okay, it is a very, 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 very fast motion, while the crawling motion is becoming even slower and slower. Because the crawling motion, there is a mu factor which is coming here. So eventually, what happens is that what is the asymptotic curve that you are going to get to? The asymptotic curve will be this curve, ABCD. You are going to get to a periodic curve, which is this one. This is asymptotically. Does that mean that any initial condition, by the way, first comment is, whatever I said, that asymptotically you go to this curve and the motion that, it is true for like any point that you start out from inside of this region. You will be pushed out to this closed trajectory, and the reverse will be true if you are outside, then you will be pulled in. Now when I say that asymptotically you approach this closed curve, does that mean that any initial condition, trajectory starting from any initial condition, will eventually coincide with the closed curve? Is it possible? First of all, did you get that there is a closed curve that is the limiting curve for everything? ABCD, 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 ABCD. That it is a closed curve that it will eventually approach asymptotically. Does that mean it approaches that curve, but can it actually coincide with that curve? You understand the difference between approaching someone and coinciding, right? X going to 0 is not the same as x equal to 0. In the same way, I am asking, the closed curve that it approaches is ABCD. Could it be also the curve that it actually, takes up the form of in the long time limit? Is it possible? Why? No, a closed curve is, it can just go on and on. If you start on a closed curve, it can just go on and on. But what I'm claiming is that I'm starting from one initial condition and eventually I'm approaching this closed curve. Is it possible that, let me just draw it a bit big to, of course, this will also introduce the notion of a stable and a limit and an unstable limit cycle. What I'm saying is that there is some closed curve. Let's say the closed curve is of that sort. This closed curve is A, B, Please excuse my drawing because I'm not very good on that, or I don't have the patience to draw it perfectly. Maybe that's the right way to say. What I'm saying is that you start from some initial condition and eventually you approach this one. You go out and, but what I'm saying is that can it actually coincide with this one? It is not possible. Why? Because my differential equations are first order in time. For every initial condition, there is a unique final condition. So it can only approach it, it can never coincide with it. Okay? And this closed trajectory that you get, which is the limiting curve for this dynamics, is what is known as a limit cycle. Why it is called a limit cycle? First of all, let's see why is it called a cycle. It's called a cycle because it's a periodic orbit. If you start exactly on this closed curve, you keep coming back to your starting point after a certain time, which is the period of the cycle. Okay, that's why it's called cycle. So let me just write the word limit cycle. Cycle we understand. Why is it called limit? Because it is not the actual curve that you get to. It is the curve that you approach asymptotically. The longer you wait, the smaller will be the deviation between your actual trajectory and the limit cycle. I wait for 1000 years, the separation becomes 10 to the power minus 56. If I wait for a billion years, the separation becomes 10 to the power minus 10 to the power minus 10 to the power minus 56. So therefore, I only approach it, and therefore for all practical purpose, if I have to study the dynamics in the long time limit, I better know how does one characterize the dynamics on the limit cycle. Because I'm pretty sure that eventually in the long time limit, my actual trajectory will be very, very close to it, and therefore the dynamics can be approximated to a good way by the dynamics on the limit cycle. Dynamics close to the limit cycle will be close to the dynamics on the limit cycle. Of course, it is easier stated than done, and it requires the introduction of the notion of isochrones that I will do in the next class. But I hope the limit cycle part is okay. 5 minutes, right? Yeah. Yes, yes. Yeah. No. Mu is fixed. Initial condition means the value of, okay, let me see. So initial condition means, initial condition means suppose you are given a differential equation. You don't play with the parameters. No? You keep your parameters fixed, but then you change the values of the dynamical variables. Here initial condition means mu is fixed, but let's say I do the dynamics with let's say x and y. So x0 equal to 5 and y0 equal to minus 52.3. This is my initial condition. Maybe yours is x0 equal to 56 and y0 equal to whatever. 72. Yes, of course. The shape of the limit cycle will change. As I showed in that plot, that for mu small, and this is also worked out in the notes. When you see when mu is okay, let's see when mu is 0, okay, then what you have is you have this simple harmonic oscillator. You don't have any limit cycle. You have all these circles or like ellipses, and you don't have this notion that whatever initial condition you start out from, you get to a limiting curve. That possibility is not there. So when let me just mention it quickly. So when mu is equal to 0, okay? When mu is equal to 0, then you have all these concentric circles or ellipses, depending on what is the value of your different parameters, x and y, okay? This is when, and these have these ellipses, they have the property that if you start from this initial condition, you remain on this one. You cannot jump to another one. It's impossible, okay? This is plain and simple harmonic oscillator. Now when mu becomes not equal to 0, let's say mu is very, very small, 0.001, then you have a limit cycle, but then what happens is that the limit cycle will be something like this. It will be almost a circle. So the limiting curve that you get is almost a circle. it's 1 plus order mu square. It's actually worked out in the notes. You get to almost you get to a limit cycle which is almost a circle. Okay, and as you make mu larger and larger, then the circle starts distorting and get to this type of thing. The circle, it becomes more bent like this. It is no longer a circle. And in fact, that is the reason why I urge you to go through the notes for mu much smaller than 1 to see if you can understand how does one get to the form of the limit cycle. You will find that it is almost a circle, but not quite. Okay? And when mu is equal to 0, there is no limit cycle. It is impossible because mu equal to 0 is a linear system. No, no, no. For mu equal to 0? Mu not equal to 0, exactly. It doesn't depend on the initial condition. Of course, when I say it doesn't depend on the initial condition, there is a caveat, namely to say that, I cannot start from a very atypical initial condition. Let's say, my x and y are here and I start somewhere in Galileo. Then, of course, you have to wait for very, very long to come back. But let's say for most initial conditions, it is true that the eventual long time asymptotic curve that you get to doesn't depend on the initial condition, unlike what is the situation when you have a simple harmonic oscillator. Okay? Maybe it's time to, okay. Yeah. Whichever order. I hope you commute, so it doesn't matter. Sure. What? Sorry? How do I know the step? The way you argued, that you see x dot, it is large until you come very close to the curve x is equal to fx. Because on this curve, x is exactly equal to fx on this curve. X dot is 0 exactly on this curve. So when you come very close, x dot will be small. And if x dot becomes small, then y dot takes over. And y dot pushes it down. But then it cannot go all the way down because at some point x dot will take over. And then it would push it. And then y dot will bring it down and push it and so on. It's just a form of these equations. You see, x dot is very large because there is a mu sitting here unless x is equal to fx. Right? Because if x is equal to fx or if x is very close to fx, then this term is close to 0. It doesn't matter what mu is. Okay? You think about it because you may not get it, so you think about it and catch me later if you are still interested in it, because it's something that you have to develop a feel for it. It's just a form of these equations that make it. Please do spend some time, maybe after lunch and so on. And if you are in doubt, then the best thing would be just numerically integrate the equation of motion and see what does the trajectory do. Because computers don't lie, I would think. I may lie, but computers don't lie.
So why is there some variable that we have defined to solve the equation, but it does not necessarily imply velocity or something else. So here it does not have a physical meaning.
Yeah, because it is not a Hamiltonian system. Because you see, first of all, you have you have damping, so it cannot be a Hamiltonian system. And secondly, these equations of motion you cannot derive from some underlying Hamiltonian. And so it's just a nonlinear dynamical system in the sense that it's an equation of motion that has the feature that, and by the way, Hamiltonian systems also would not work because Hamiltonian systems have this conservation, the energy conservation. So therefore, if you perturb, you will go to another orbit. You cannot just come back to the same. Here, wherever you start out from, in fact, this is the picture that I have, that if you have a limit cycle, you start from here, you eventually come there. You start from here, you eventually come there. It's the notion of fixed point, but then which is generalized to higher dimension. Point is one point, stable fixed point. Wherever you start from, you come there. Here, instead of a point, you have a curve, a trajectory, a closed curve to which you are pulled in wherever you start out from. Okay, thank you. So how about